Okay, we are going to embark now on what is widely considered the most difficult topic in Algebra 1. Systems? No, actually systems is actually, the thing with systems is that since the problems tend to be longer, you're more susceptible to careless mistakes, but as far as comprehension goes, systems and equations is not really up there. For some reason graphing, I say graphing maybe the second most.
I'm good at graphing.
This is widely accepted as being kind of like you hear Algebra 2 teachers say, hey, my kids still don't know how to factor. It's not meant to scare you. It's very doable. I have kids that do perfectly fine. I'm just telling you this more to also one of the monkey wrench that's getting thrown right into the middle of things is we're gonna have a week off. I'm gonna give you a quiz on Thursday right before you leave. And hopefully, if you notice the week 12 assignment, for this week that you will not have class time to work on it this week. I don't have the computers this week, but it isn't due until the end of spring break. So like you don't have a spring break assignment per se, but this week's assignment it won't be due until that Sunday after. Not this coming Sunday, but the Sunday afterwards. All right. Oh, you like on the road and you spin the thing and,
No, I didn't do that.
and then you dance with it. All right, so we need to focus on what is factoring, right? Well, we're gonna deal primarily with expressions. We are gonna throw in a couple of equations on Wednesday, but these deal with expressions. Think of expression as like half of an equation. No equal sign. We're not solving. What are we used to doing with expressions? If equations get solved, what are you used to doing to expressions? The quicker you answer, the quicker we finish. And whatever. We don't solve expressions. What do we do to expressions? Simplify. Normally we simplify. Okay, we do order of operations, we distribute, we combine like terms, we simplify, right? So I think part of the thing, like where it helps to establish, and then one of the things I'm going to emphasize throughout, is that factoring is the opposite. Sadly, you guys don't think of problems as being skill specific. You don't think of you don't look at a problem and say, oh, here I'm factoring, here I'm simplifying, here I'm solving. You just think of it as problem and answer. Well, what you're gonna see now is since you're used to simplifying, what you think of being the answer is going to be the problem. And you just gotta go backwards. Okay. The main type of and I want to say I filtered these down, but maybe one of them got by. We're going to factor quadratic expressions. We learned that word at the beginning of the semester. What does that adjective mean when you call an expression quadratic? We used the word polynomial before instead of expression, but you say tomato, I say expression. What does that adjective mean? It does not mean 4. What does quadratic mean? Feel free to go back through all those notes that Papa Romero was nice enough to print for you and put holes in so you could just stick inside the notebook. One thing we do have today is time. Gotta love that. Tick tock, tick tock, tick tock. No. Let her sleep. No. You guys have a week to sleep next week.
No, I don't. I have to get up for the children.
Oh, and Hope has to hold signs with arrows on them.
No, I don't.
You're done with them?
Yeah, I'm doing it. I think that's a lot. lot of them.
Yeah.
Some people probably got fired.
On your mark and set, check your notes. Go. Beginning. When we did naming polynomials at the very, might have even been the first lesson of the term. Back when you used to care.
Yeah, that's definitely.
That's so creepy. This looks like a scary movie. That's scary.
Have you seen? I want to see that movie.
Oh yeah, same.
Was it scary?
What is that? Quadratic.
There you go. Good job, Isaac. You summed it up perfectly. The Pet Cemetery one also.
That sounds, yeah. Heather, come back with every time.
Seriously, it takes you guys that long to tell me what quadratic means?
Okay, it's a long time. Quad. What is
What day
a
does
quad?
school end? Mr. Man, you know how many notes you want?
Look at all this. I mean, I found quadratic graphic.
Huh?
So hot. They're being polynomials.
Yeah, there it is. I see it. I seen it. I seen it.
Stop. Oh.
Oh yeah.
Oh. It's when it has four.
No, not 4 terms.
Degrees.
4 degrees.
Not 4 degrees. The word quadratic is not next to a 4 anywhere. You sure about that?
Polynomial.
Come on.
Oh, look at that. Oh,
And what is that next to? What is that next
Oh, 2. Oh, okay.
Quadratic is when your expression has a 2 as the biggest exponent.
Okay.
Yeah, I'll mention. Okay. When the biggest exponent is a 2. So that's important. So when we have an expression where the biggest exponent is a 2, what we want to look at next is the number of terms. Because that's going to tell us how we're allowed to factor. The first thing we always look for first is if the terms have a greatest common factor. Okay. Then whether or not we have a greatest. One other thing you might want to jot this down. We talked about how factoring is the opposite of simplifying. So I could be specific and tell you what specific type of simplifying each one is the opposite of. Greatest common factor is the opposite of distributive property. When you are factoring by greatest common factor, it'll feel like you're backwards distributing. So that sound I hear is everybody writing down that in all that space you have that GCF is the opposite of distributive property. Okay. Now, if you have 2 terms, there's one other thing that we can try for, and that's to see if our expression is a difference of squares. You know it's on the paper right in front of you too, right?
Oh, wow. I'm exactly down. Way down.
Well, I didn't write anything else. I just said that GCF is the opposite of distributive property. Difference of squares is considered a shortcut. It's when you factor by formula, you're factoring by substitution. I'll show you what that means. With 3 terms, we can have what's called a perfect square trinomial. We'll talk about that in a second. That usually doesn't work. And then, in my opinion, when I say that factoring is so challenging, this is the big one here, the factor chart. I use a table, like a chart, in order to factor. Some kids that come from other teachers tell me that they use this like X method thing. So if you had a teacher before that did that and you feel comfortable, you'd be my guest. I wouldn't be so opposed to it, but not one person, teachers included, have been able to show me how this is somehow more thorough than the one I use. You know, from what I can tell, it requires heavily on mental math, and that's not one of our strong suits. But be my guest. Occasionally, oh, but the X is so much easier. Fine, do it. I don't. If it made sense to me, I would do it, but it doesn't. So I'll do it. I'll show you the way I do. Now with 4 terms, there's a method called grouping, but I don't know if it's a Gwinnett thing. I haven't seen it covered in any of the stuff that in any of the materials we have. So we won't worry about grouping. The only thing we're really gonna factor here are either 2 terms or 3 terms. You won't have to worry about 4 terms. If nothing works, if you are not able to factor an expression, that expression is said to be prime. So the first slide talks about the shortcuts. If you are going to factor an expression as a difference of squares, what does the word difference mean in math? Subtraction. So remember, what you're used to seeing as the answer is now going to be the problem. If you have an expression where you are subtracting, where one of the terms are negative, and when they say squares, they're talking about perfect squares. What are some perfect squares? What numbers do you know to be perfect squares? 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225. Huh? Now, that's all fine and dandy, but here's where that paying attention part comes in. I'm going to ask you this over and over again. What does a difference of squares look like in factored form? I'll see, you might have to come up here if you're blind today. Those are called conjugates. You're going to hear that word over and over again. Conjugates.
Oh, I remember this.
You remember conjugates? Conjugates are just 2 binomials where the only thing different between them is the sign in the middle. Don't get turned off right now, like, because I know that we don't think well abstractly, like, what? I don't get it. A's and B's, forget it. It's too hard. Not yet. I'm just trying to like to give you a little bit of an explanation. Okay, then we also have what are called perfect square trinomials. Perfect square trinomials are very similar to difference of squares. The only difference is that, no pun intended, that there's 3 terms. But now the perfect squares are at the beginning and at the end. There's a couple, see, the nice thing about perfect square trinomials is that they possibly can save you from having to do a factor chart. Not always, and if anything, I would say rarely, but if it works, it'll definitely save you some time. And it doesn't take that much work to check. A lot of the check is visual. Okay. The first and last term, if there's 3 terms, the first and last term has to be not only perfect, but also positive. Okay, is it positive? Is it perfect? And then the middle term has to be equal to 2ab, but there's an easier check. This is something else that you can write down, Elsie. There's another check you can do, and that's a check to see if b squared is equal to 4ac. Okay, now another difference between this and difference of squares. In factored form, you still have 2 binomials, just like difference of squares does. David, you mean to hold on to that for you? You don't have that's not a phone that you're holding on to on your lap there? Oh, thanks, man. Appreciate it. I was just wondering why you had your head down and then you got your head up. I doubt it was conjugates that got you to get your head up, so I figured it was your phone. I apologize. Yeah, you had your head down on the table before, and now it's up. So maybe you just like conjugates. For perfect square trinomials, there's still two binomials, but it's repeated. Like what's another way of saying something squared? When a number is squared, what are you really doing? Multiplying by itself. So a plus b squared is the same as a plus b times a plus b. Instead of like in conjugates where having different signs, they have the same signs. How do you know what sign is there? The sign in the middle. I know it seems confusing, but it's not as confusing as what you start seeing examples, so it'll make more sense. And then finally, the main course, the factor chart, right? If we have a quadratic expression that's in standard form, a is the number in front of x squared, b is going to be the number in front of the x, and c is a constant. The way we want to try to factor is, when I say AC, what am I talking about? Not air conditioning. In algebra, when you put two letters together, what are you doing? Multiplying. So get A times C and put that number on the top. Like I'm going to do a 2-column table. Put that number on the top of the left column. B just goes on the top of the right. Think of the left column as being a multiplication column. Think of the right column as being an addition column. So I want to see what pair of numbers I can multiply to get the number up here, and then see which one that same pair will add up to whatever B is. Tim, I started off this lesson by telling you that factoring is widely considered to be the most challenging aspect of Algebra 1. What I didn't tell you is why. Now, this is a bit of an opinion, but I think it's a pretty strong opinion. Why do you think people struggle so much with factoring? What basic math skill do you think is a necessity that yet a lot of us do not have? Say it again. Somebody said something? Counting? Did somebody say counting? No, it's not counting. Exactly right. Exactly right. Our times tables. Times tables, yeah. Now, the nice thing about using this table like I showed you is that if you are willing to listen, I feel this is more methodical than that X method is that I told you that that some other classes do. This X method relies more on mental math, where somebody who is disciplined can in fact use the calculator that we're so reliant on in order to do this table. But one of the annoying things is that it gets long. It can get long unless you can. Eventually, you should be able to do these in your head most of the time, but at least at the beginning, it can get kind of long. So to make our life easier, Papa Romero has taken care of you and gave you like a cheat sheet. We can limit the size of our table by looking at signs. So let's look at the first scenario. Okay, just remember, well, we're looking for two numbers. Okay, we're looking for two numbers, number 1 and number 2. We're looking for two numbers here, right? If I remember the AC column is multiply. What are the only ways that I can multiply two numbers and get a positive? That would be the obvious one if they're both positive, but also, what's the other way I can multiply two numbers and get a positive? If they're both negative. Positive times positive is positive, negative times negative is also positive, right? But if at the same time, simultaneously, you have to get those two numbers and add them and get a positive, what's the only way that could occur? Yeah, they're both positive. You cannot add, some kids might tell you otherwise, but you cannot add two negatives and get a positive. If I have to multiply two numbers and get a positive, but at the same time, Xavier, get those same two numbers and add them and get a negative, what's the only combination of numbers where that's possible? if they're both negative. You're gonna have all spring break to study this. Okay, if I multiply two numbers and get a negative, what's the only way that that can occur? What's the only way you can multiply two numbers and get a negative? No. One's positive and one is negative. But now, once I have those two numbers, okay, one positive, one negative, if I have to add them and get a positive, what else has to be true about those numbers? The bigger one has to be the positive one. Small negative, big positive. And then finally, the last one. If you're multiplying and adding and getting a negative both times, you have to have one positive, one negative, but the bigger one has to be negative. All right, the moment you've all been waiting for. Let's put that into practice now. Let's get started. Let's begin to factor. When you factor, remember, see, like, still no phone? Your stuff can't handle it? No, I can do whatever I want. It's my classroom. You look at this and you're like, wait, but what do you want me to do? I don't get it. Like, there's no like terms there. I can't, well, yeah, but we're not trying to simplify. We're trying to go backwards and factor. So what we want to do is identify how many terms. How many terms does this have? 3. Okay, there are 1, 2, 3 terms. What do you look for first when you have 3 terms as far as factoring? I gave you a table at the very beginning. What factoring method do you always try to do first when you have to? Greatest common factor. Here, if you're paying attention. If your expression is quadratic and you have a 1 in front, you're not going to have a greatest common factor. You can just skip it. It's not going to work. Okay?
No resolution.
Well, we're not solving anything. So, nothing about solutions because we're not solving. There's no greatest common factor here. There is no one common number that I can divide all 3 of these terms by. So we move on to the next one. What's the next one say? Perfect square. Let's check and see if there's a perfect square trinomial. The nice thing about it is that the half of this is visual. Huh? Yeah, 3 terms. So perfect square trinomial. Are the first and last term positive? Yes. Are the first and last term perfect? Yes, they are. What times itself gives you y squared? Y. Y times y is y squared. What times itself gives you 36? 6. So the second check would be to say, all right, if this number in front here is A, this is B, and this is C, let's do B squared. So 15 squared would have to be equal to 4 times A, which is 1, times C, which is 36. 15 squared is 225. 4 times 1 times 36, is that 144? Are those two numbers equal? No, it's not, so it's not a perfect square trinomial. So you might say, Mr. Romero, that's 15 seconds of my life that I'll never get back. How dare you waste my time like that? If it would have worked, it would have saved us a lot more time. Okay. So, before we can just say that this is prime, meaning that it can't be factored, we do have one more option. It's the evil option, but we do have one more option. Not a factor tree, but what I call a factor chart or table. Let's see, A is 1 here, B is 15, and C is 36, right? So what is A times C? 36. B is 15. Just pay attention this time around. Maybe it'll be easier. It's too much for you to know what 1 times 36 is?
Yeah.
Because the first column is A times C, the second column is just going to be whatever B is.
Okay.
Okay, so we're going to start off with the multiplication column. Here's where the times tables come in. Okay, whether you do it mentally or whether you have to like do it methodically by using a calculator, 36 divided by 1, 36 divided by 2, 36 divided by 3, 36 divided by 4, you have to think of every combination of numbers that you can multiply to get 36. Don't worry about signs yet. So 1, 3, 12, 9. That's every combination of numbers that you can multiply to get 36. But now to try to make your life easier, because signs do play a role, I gave you a table that says, hey, when the numbers at the top are both positive, what's true about our factors? Sandra? Yeah, they're both going to be positive. So I'm going to then go back and make all of these numbers positive, 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 positive. Now the $1,000,000 question, and what's going to ultimately prove if I can factor this or not, is do any of these combos, do any of these combinations add up, because this is now an adding column, do any of these add up to 15?
Yeah.
Which one?
3 and 12.
3 and 12 do add up to 15. So hip hop hooray, ring the bells. Isaac's excited. Oh, studies have shown that factoring is much easier if you keep your head up. Later on, you don't complain about how hard it is. Since 3 and 12 is our winning combination, okay, now we have to check one more thing. Okay, we got to go back up to here where we identified A, B, and C. If A is 1, which it is, you can go straight to factored form. If A is not 1, you got to do a little bit more. But luckily A is 1. I'm ready to factor. Here come the factors. Ready? It's going to be 2 parentheses always. Whenever you have a table, it's always going to be 2 parentheses. The numbers that you just found are going to come second. So plus 3 plus 12. Those are the numbers I just found. Because A was just 1, then at the beginning, you just put the variables in here. So what does this mean? This here is the same expression as that up there. The only difference is at the top, we were given it in simplest form. At the bottom, it's in factored form. Wait, but now what are we supposed to do? Are we supposed to FOIL that? Well, no, because if you FOIL this, what's going to happen? We're going to end up back to where we started. We're just going backwards. That is, yes, correct. Now the question has become the answer. Rubencito, chiquitico, pobrecito. Ruben, hey, wakey wakey, man. So, Xavier wants to stare deeply into your eyes. All right, how many terms do I have here? Okay, we do have 3 terms, so what do we look for first? Okay, is there a greatest common factor? Just real quick, what's A here?
-1.
-1. Good. What's B?
3.
And what's C? 40. I told you when you have a quadratic that has a 1 in the front, you're not going to have a greatest common factor. But if you have a negative in front, factoring is just it's not going to work out very well. So what we're going to do, even though it doesn't appear we have a greatest common factor, we're going to pretend like we do. We're going to factor out that -1. Factoring out a -1 does the same thing that distributing a -1 does. In the past, what did you remember happens when you distributed a -1? The signs change. So the same thing is going to happen here. X squared becomes positive. Now we have a -3x, and we have a -40. That minus is going to stay in front the whole time. But now my A, B, and C change. Now my A is +1, my B is -3, and my C is -40. There is no more greatest common factor. Could this possibly be a perfect square trinomial? Why not? In order to be a perfect square trinomial, the first and last have to be positive. Are the first and last positive? No, 40 is not so. I don't even have to worry about it. I don't have to write anything down. I don't have to write down b squares. Keep on moving. Elsie, question?
You don't have to like make a chart.
Well, not this. Then that will come last. Not now comes the chart. Yeah. Chart. What is a times c here? Negative 40. And b is. Let's not worry about signs yet. And Mr. Romero says, all right, let's think of all the numbers all the combinations of numbers that we can think of that multiply to give us 40. Okay, so 1 and 40, 2 and 20, 4 and 10, 8 and 5. That's every combination. Okay, now we're bringing the negative. As long as we can memorize the table I gave you. Well, let's see. When the left column, when the AC column is negative and the B column is negative, what was the distribution of signs? How should the signs be arranged? Small positive, big negative. So go back and make all the smaller of the two positive. Make the bigger of the two numbers negative. And then Lana comes in and says, all right, do any of these add up to give me -3? If none of them do, then we have prime. I'll give you a clue. Don't expect to see many primes on the testing quizzes. Yeah, 5 and -8. Okay, once you finish and you found your winning combination, go back and look at A. Is A1? Is A1? Yes, it is. So that means I can go straight to factored form. But the only reason that A is 1 is because I factored out that negative in the beginning. That negative still has to be there. You can't forget it. That's the negative that came out of the beginning. Then the first term in each one is just going to be the variable, which is x. The second term is going to be the number that I got from the table. Wait, but Mr. Romero, how about if I put x minus 8 first and then x plus 5? That's fine. The order of the parentheses doesn't matter, but the sign does. So if you were to put like x minus 5 and x plus 8, that's wrong. Huh?
I've done this 3 times.
Well, one thing at a time. I've only done 2 examples yet, so you're still, yeah. How many terms do I have here? 2 terms. Okay, so what do I look for first? Do I have a greatest common factor here? Can, yes, very good. I'll see both of these terms can be divided by 3, so I bring out a 3. That gives me a squared plus 3. But think of GCF as being independent from everything else. Whether or not GCF is successful, that doesn't mean that other things can't work as well. So if after GCF, I still have 2 terms left in the parentheses, and I want to see if those can be factored any further. Well, what's the only other method I have for 2 terms? What's the only other method I have for 2 terms? I told you at the beginning that the more you respond, the quicker difference of squares. Could this possibly be a difference of squares? No. It's not even a difference, so we're done. What you see there is our answer. Wait, but Mr. Romero, wouldn't that be prime because nothing worked? No, it's not prime because something did work. What worked? GCF worked. GCF worked. So it's not prime. That's it. That cannot be. Most of these questions are going to say on it, factor completely. This has been factored completely. I cannot factor this anymore. What other thing? No chart because the chart is for 3 terms. There's only 2 terms. You don't have
X plus 5.
the x plus 5 thing?
But we're only looking for the last.
No, this is already factored. Look,
It's because I have two
here's another thing that you can think of, okay? What symbol is most associated with factoring? Like when you look at an expression that's in factored form versus you're gonna need this, but no one what's the symbol that shows up when something's in factored form? The parentheses. So LC, do I have a parentheses already? Yeah. Now that doesn't mean that you might not be able to factor more, but in this case I can't factor anymore. The parentheses are there. This is factor. What's the answer? The answer would be again 3 squared. That is factored form. Okie dokie, artichoke. All right. Here we go. How many terms? 2 terms. What do we look for first with 2 terms? Okay, greatest common factor. Do I have a greatest common factor here?
Yes. 1. No, you don't.
No.
Yes, you do.
0.
Greatest common factor. There's only something that both of those terms. Yeah, fine. Yes, but 1's always going to be a common factor. Anything can be divided by 1. So like you're never going to see us bring out a 1. No, 2's not going to work. What do both of those terms have? Thank you. Common. They both have an X. So my greatest common factor here is X. They each have at least a single X. If I bring out an X, maybe I didn't emphasize this enough on the last problem where we had a GCF. But what you're really doing is dividing each term by the greatest common factor. Like look on this last one, right? What is 3a squared divided by 3? It's a squared. What is 9 divided by 3? 3. We talked about how simplifying and factoring are opposites. I don't want to distribute, but if I did distribute here at the end, what would I end up with? What I started with. So let's go to this one, right? X times what gives you x squared? X times x. So that would be the first term. X times what gives you negative 2x? No, x times what? Negative 2. And now we're done. Sure, because the only thing that you can do that's left is factor whatever's in the parentheses. But that's linear. Like when you don't see an exponent in there, you're done. Now, the only possible way that you wouldn't be done is if you did not bring out the greatest common factor. If you brought out a common factor that wasn't the greatest common factor, there might be more left in there to factor, but I brought out the greatest common factor. Alrighty, how many terms? There are 3 terms here. By the way, this will be the hardest type of problem that you'll get. If you can understand this, you'll understand everything else. It has the most amount of steps. And I'll explain to you also why it's the quote-unquote hardest type. Besides the fact that it has 3 terms, there's also something else about it. What do we look for first? Okay. Let's identify A, B, and C. Okay. What's A here? 14. What's B? Okay. And what's C? The reason why this is a challenging one is because of this. On the ones that we've had before with 3 terms, A has been 1. Anytime A is greater than 1, it requires more steps. But sometimes this gets remedied by GCF. Sometimes the GCF takes care of that for you. And this one, it won't. But there is a GCF, though. And we like GCF because GCF makes our numbers smaller. And when we inevitably end up in a chart, we'd rather deal with smaller numbers than bigger numbers. So can anybody tell me what that greatest common factor is? What's the biggest number I can divide all those terms by? Very good. So I do have a GCF of 7. So now I bring out the 7. 7 times what gives me 14y squared? 2y squared. Good. 7 times what gives you 7y? Oh, y. 7 times y.
Oh.
7y. Did I say squared?
Yeah, no, you just
7y.
said 7. What times 7?
What times 7 gives you 7y? Y. 7 times what gives you negative 21?
Okay, here's a longer way to do it. You like do A times C still, and then do
Well, I'm getting there. I'm not done yet.
not done yet.
Nope.
You still do it.
I have to still do it. Have I factored? Yes. Have I factored completely? No. Okay. So I gave you a list to follow, right? So right now we did GCF. What's the next thing we look for with 3 terms? No. Perfect square trinomial. See, but I know for perfect square trinomial, the first and the last one have to both be positive. This 3 is negative, so I don't even need to waste my time. I can skip it. Okay. And then yes, Elsie, we've reached our table, but now our A, B, and C values have changed. What's A gonna be? Or just the 2, the number in front. Well, B is the number in front of the Y, which is 1, and then C is negative 3. So here we go. What is A times C here? And then B is 1. Luckily, by doing GCF, that made my my number smaller. So it shouldn't be that hard to think of what numbers multiply. Now, don't worry about the negative, but 6 is just 1 times 6 and 2 times 3. Under this scenario where you have a negative AC column and a positive B column, what did I tell you to do with the signs? Yes, Elsie? No, the biggest one positive. In this scenario, when it's negative positive, it should be small negative, big positive. Do any of these add up to 1? Do any of these add up to positive 1? Yes, they do. Negative 2 and positive 3 adds up to 1. Yay, we had great success. Now, what I'm about to show you is a shortcut. Years and years ago, when I, maybe had a little bit more steam in my engine, I used to try to force kids to learn the appropriate way to factor these, which was a method called grouping. Okay, that you can apply grouping to 3 terms, but that required not only a little bit more math, but paying attention. And since half of you are asleep right now, that's not going to be very effective. So watch here. Here's a shortcut, okay? Elsie, if you remember on the ones before, that you even asked me, like, oh, you're not going to do those parentheses things? Yeah, look, I'm going to go ahead and do the parentheses things. But the thing is, I'm not going to be done. There's still more to do after this, okay? But so far, have I lost you yet?
No, I'm doing.
Okay, but have I lost you yet?
No.
Okay.
I already did that.
Now remember also that we had a 7 in the front. That 7 just drops down. Have I lost you yet?
No.
No. Now ready? Here we go. Because see, and I firmly believe that this is a paying attention thing and not a math thing. Because I feel the feeling I get is that kids are like, hey, my brain is full right now. No thanks. No more space. I don't want. It's just one extra little step. Because what I get is I get kids that eventually, just through attrition, I force them to learn this, but then they just say, okay, cool, y minus 2, y plus 3, and they did everything right, but then they stopped there. Well, that's wrong. Yeah, well, but yeah, because you haven't learned the extra step yet. But it's a shame if you can get this far. Why not just pay a little bit more attention? Okay. See, because the thing is, remember that we let off by saying that A is not 1. So here's the trick. Get that number, whatever that number is, and write it in front of the y. Get whatever the number that's an A, and write it in front of the y, which I guess technically you've been doing all along, because when A was 1, you would leave it in front of the y. You wouldn't do anything with it. Just you wouldn't need to write it. But in this case, now by doing this is a shortcut. This is not really sound, but I haven't been able to disprove that it works. So go look at each parentheses, and if any of the parentheses have a common factor, you have to throw it away. Like you don't actually keep it like you did with the 7. You just throw it away. Look at the first parentheses. Do the two terms in there have a common factor? Can they be divided by the same number? Yes, obviously. What can they both be divided by? No, look at the first parenthesis. What can they both be divided by? Let's say it, I'll see. 2. So we're going to divide it by 2. We're not going to do anything with the 2, but we're just going to just throw it away. Look at the second parenthesis. Does that have anything in common? No, it does not. So we're just going to drop it down. So let's see. Watch. The 7 dropped down. The 2y plus 3 dropped down. But the only thing that ended up changing was 2y divided by 2. Okay, which is y. And then what's negative 2 divided by 2? No. If you could just remember that extra step. Yeah, that's it. No. We still have two examples. I see. Look, the people that have had their heads down have had their heads down since the first 5 minutes. So, don't give me this thing about 3 hours or 2 hours. If you do pay attention, we should be done by the end of the second hour. I firmly believe, where you would still have somewhere in the neighborhood of 30 to 45 minutes, maybe, to decompress. But I asked you at the beginning, the more that you participate, the quicker I go. Yet I've had 3 or 4 people that have contributed consistently. Yeah, exactly. Yeah, welcome to my life. How many terms do you have here? 3. The first thing we look for is the greatest common factor. Do I have one? No, I do not. Okay, so I identified A, B, and C. You're gonna like this one. The good news, Elsie, you seem eager to go to the factor chart. If you do a factor chart, it'll work. Okay, so you don't necessarily have to learn the shortcuts, but the shortcuts do help. Okay, are the first and last term positive? Yes. Are the first and last term perfect? Because this has to be true. You just can't randomly do it. Yeah. Yes, they are. What times itself gives you x squared? What? X. X times x is x squared. What times itself gives you 1? So now you can do that check where I said b squared. B was 2, right? So 2 squared would have to equal 4 times a, which is 1, times c, which is 1. 2 squared is 4. 4 times 1 times 1 is 4. Yay, look at that. We have a perfect square trinomial. So now instead of having to do a chart, we can just factor by a formula. Ready? Here's the formula. It's always going to look the same. It's going to be 1 parentheses. Perfect square trinomial will always be 1 parentheses with a square on the outside. People get these confused with conjugates. These are not conjugates. It's 1 parentheses. The sign in the middle of that parentheses is going to be the same thing as the sign in the middle before. What was the sign in the middle at the beginning? So this is still going to be positive in the middle. And then we talked about how the first and last term were perfect squares, how they had to be a perfect square. Just take the square root of each one and put them on each side. For the second time in the last 30 seconds, what's the square root of x squared? Like what times itself gives you x squared? What times itself gives you 1? Ta-da, done. If you would have done the table, Elsie, instead of getting it like this, you would have gotten x plus 1 and x plus 1. That's what you would have gotten. But now, you might be thinking, oh yeah, look at that. Well, what type of shortcut is that? It took forever. Well, it's because I had to explain it. I could have done that in 5 seconds if I wanted. Okay. How many terms? No, Elsie, no. Come on. Come on. Remember the alternatives. Remember where else you could be here today. So, but we do have 3 terms. Do these have a common factor? I told you anytime that we have a quadratic with a 1 in front, there's no common factor, so don't worry about it. What's A? What's B? What's C? before we go do a table, let's see if we can save ourselves some time. Don't have saving yourself some time. What are the first and last positive? Yes, are the first and last perfect? Yes, so now let's go do the check. B squared, which would be negative 18 squared, would have to equal 4 times 1 times C, which is 81. B squared is equal to 4AC. Negative 18 squared. I know negative times negative is positive. Somebody have a calculator? 18 times 18? Please, pretty please. 18 times 18. I'm guessing it's going to be 324. I'm pretty sure these two are equal. Yeah. 324. So for the second time in a row, I have a perfect square trinomial. So for the second time in a row, we're going to have one parenthesis with a square on the outside. What sign goes in the middle? In this case, since we had a negative before, that just drops in the middle. What's the square root of k squared? What's the square root of 81? 9. If you forget to do this and you do a table, you should get the same answer. It would just show up as k minus 9, k minus 9. Yeah, we're going to like this one too. How many terms does this have? Only 2, right? Do I have a greatest common factor here? No. So here there's no need for an A, a B, or a C. It's just either going to be greatest common factor, yes or no. And then if not, or if not, doesn't matter. Could this be a difference of squares? Well, do we have a difference? Yes, we do. Do we have 2 perfect squares? Can I multiply some term times itself to get 4x squared? Yeah. What? What times itself gives you 2x? This is 2x squared. What times itself gives you 49? 7. All right. So with the difference of squares, this is where I wrote down. So of course you also wrote down conjugates. This is also considered a shortcut because it's just substitution. I would get these 2 little bobbles right here, and I'm going to have one parenthesis with a plus in the middle, one parenthesis with a minus in the middle. That's where the conjugates are. At the beginning of both of them goes to 2x, at the end of both of them goes to 7, and now I'm done. Those are called conjugates. All right. Conjugates.
Okay, next time,
Well, I just want to make sure you understand it.
We understand.
let's just have to try ourselves.
Okay. Well, see, this is slightly different. Can anybody tell how this expression is different than any of the other ones I've had so far? Very good. It's not quadratic. There's no square. So if there's no square, then all we're looking at is GCF. Either it's going to be GCF or it's going to be prime.
Okay. There is.
It definitely has to be a GCF because both of those numbers are equal.
Yeah, there should be.
So what's the biggest number I can divide both of those by?
Yeah, it's one of the biggest.
Yeah, it's going to be 4. Now, if you use your 4 as your GCF, I don't have a problem with it. That's fine with me. But most books, instances, I give you stuff multiple choice, and the book is the one that chooses the answers. You'll probably see a negative GCF because they don't like to leave a negative in front. So if I were to use a negative 4 as my GCF, negative 4 times what? Gives you negative 40x. Well, correct. I don't have a problem with it, but you probably won't see that in your multiple choice. So I'm doing it the way you probably see it, where they would factor out a negative. Negative 4 times negative 4 times what gives you negative 40?
Negative 7.
And that would be positive 10, but keep the x. And then negative 4 times what gives you positive 28?
Negative 7.
Yeah.
And now we're done. There's no need to do anything further because this is not quadratic.
All right.
Yeah, Taiwan's on a roll. Call him butter.
Oh my gosh. Oh my gosh.
We have like
Okay. So remember I told you that a couple of these might have snuck in. This is one of them. What's the biggest exponent here? No, what's the biggest exponent here? There's a 5. You know, that's not going to really be the most important things, but let's just do this anyways.
Wouldn't it be?
The biggest exponent?
Oh,
The biggest exponent here is a 5. Being quadratic, we're mostly trying to factor things with a 2 is the biggest one. But we can fix this real quick. Because what's the greatest common factor here? Okay, Jason, they had before I said 10, but what else do they have in common?
negative.
What else do they have in common? Yeah, and how many ends? Because they all have more than one end. What's the least amount of ends they have?
3.
Yeah, so they each have at least 3 ends. So 10 ends to the third is my greatest common factor. I'm going to bring it out. 10 ends to the third. Now let's see what's left over.
Okay.
Because greatest common factor is the opposite of distributive property, the same thing with distributive property. If you start with 3 terms, I still need 3 terms. So let's do it this way. 10 times 1 gives me 50.
35.
5.
Ends squared.
5. If I had 5 ends before and I took out 3, now I have 2 ends on the inside and squared. Then I have plus another 5. If I had 4 ends and I took 3 of them out, how many ends are left on that term? 1. And then finally at the end it would be minus 2, and I took out all of the ends. This cannot be a perfect square trinomial because the 2 is negative. So when I identify, I have to do a table now. I'll see who's missing those. What's A times C going to be here? A is negative 10, and then B is 5. All the numbers I can multiply to get 10, forget about the fact it's negative, is 1 and 10 and 2 and 5. When the first column is negative and the second column is positive, yes, Elsie?
Negative first.
Yeah, small negative, big positive. But watch, do any of these add up to 5?
No.
No, they don't. So have I factored? Yes, I did GCF. So I can't say that this is prime, but in an effort to try to factor completely, I cannot factor any further, so I'm done. This over here is completely factored form. I cannot factor any further than that. I just revert back to it. How many terms?
3.
Okay. Do I have a greatest common factor?
Yeah.
What is it? It is 5. Let's bring out the 5. That gives me 7x squared plus 8x minus 10. If you don't know how I got that, let me know. Holla. I do not need to waste my time doing checking for a perfect square trinomial because the 10 is negative. So let's just do a table. What is A times C? It is negative 70. B is 8. Let's think of all the numbers we can think of that multiply to give us 70. 1 and 70, 2 and 35, 3 doesn't, 4 doesn't, 5 does. 5 and 4, 5 and 14. 6 doesn't, 7 does with 10. And that's it. Under this scenario, when it's negative and then positive, it's the smaller negative, the bigger positive. Do any of these add up to 8? Do any of these add up to 8? No, no, they don't. So what is my answer?
5 times 7.
It just stays that way. You're not gonna see anything more than that. Okay. 3 terms. Well, what do we do first? Do I have a greatest common factor here? What? 3. Very good. So once I bring out the 3, it leaves me with k squared minus 11k plus 30. Now here my first and last are positive, but are my first and last term perfect? Yeah, the k-square is, but the 30 is not. I cannot get 30 by multiplying anything times itself, so I won't waste my time with that. Let's just go straight to a factor chart. 1 times 30 is 30. Let's think of all the numbers I can think of that give me 30. 1 and 30, 2 and 15. And look, and if you can do this in your head, nobody's expecting you to have to write all these, but it's just if you're looking for something more methodical. When the first column is positive and the second column is negative, what do I know about my factors?
Well, plus and negative.
Nope. Negative, negative. When do these add up to negative 11? Yes, they do. And I even have better news for you, Elsie. Because even though we started out with a 3 in front, the GCF took care of that. What ended up being in front? You should always look at that next.
1.
A 1. So that means I can go straight to factored form. Now you can't forget that 3 that I brought out at the beginning, because that's what made this possible. Brought to you by your friendly 3 GCF. The variable was k, so it would just be k minus 5 and k minus 6. Well, wait, Mr. Romero. How about if I put k minus 6 first and then k minus 5? That's fine. You just can't make any of them positive, or hope will get you.
Thanks. Oh, go.
Here, why don't you guys do this one? Factor that completely. But that takes longer. I want this to be over. No. But you're making good progress. We only got like what, 8, 10 or 11 left?
8.
Yeah, we got time.
Got 8.
Factor that. Go on your mark. It said factor. Come on, Elsie. You said you finally understand this.
Oh, gosh.
So yeah. Well, there's not many of you that are participating actively. There is no greatest common factor. You're correct. It's just going to be a pure table, a pure factor chart.
So A,
D, E, F, G, H, I, J, K. Huh? This should not be prime.
I'm stuck.
Why do people struggle with this? Because of the times table.
I don't know why.
Is it A minus 3? Is it A minus 3 times?
Yep, that's right. A times C is negative 24. B is 5. All the numbers I can think of that multiply to 24 are 1 and 24, 2 and 12, 3 and 8. That's the big one. Because then my sign distribution here, when I have a negative and then a positive, is small negative, big positive.
Oh, see, that's what I guess.
Which one of these adds up to 5? Yeah, negative 3 and 8. And because right before this started, A was 1, I can go straight to factored form. A minus 3, A plus 8. If you write A plus 8 first and then A minus 3, that's fine. It you write a plus 3 and a minus 8 where you mess up the signs, that's wrong.
Okay, next. We'll do this one too.
Yeah, go ahead, do that one. You got it, Jonathan? Reaching for the sky. Quicker you finish, quicker we finish. Here there is a GCF. So you shouldn't have to be.
I have a spreadsheet. I mean,
Lana, you got it? What'd you get?
8 times r minus 1 minus r.
I don't think so. Actually, no, you're right. You might be right. Okay, the first thing everybody should have picked up on is that there's a GCF of 3. When I bring that out, that leaves me r squared plus 9r minus 10. So when I go, there's no need for perfect square trinomial because the last term is negative. So a is 1, b is 9, c is negative 10. So negative 10, 9. So this is 1 and 10 and 2 and 5. Elsie is here. All right. When the first column is negative and the second one's positive, small negative, big positive, why do you need that up to 9? Anybody, frankly, I mean, I guess I did address it towards you, but. So any of those combinations out to 9.
1 and 10.
It's negative 1 and 10, yeah. So, and because a was 1 right before that, because we went into this with a being 1, I can go straight to factored form. But don't forget, we brought out a 3 before. And it would just be r minus 1 and then r plus 10. And dollars. It makes dollars and cents. Okay, do this one.
I know it. I already did it.
What'd you get?
That is minus 1.
No. Oh, contraire, mon frère. Close enough. Nope.
I tried.
You did try, but you didn't pay attention to your signs. I'll see when both columns are negative. What do you do with your with the factors? What's the Small positive. Big negative.
Wait, what?
It's minus.
When both columns are negative, you got to make the smaller one positive and the bigger one negative.
That's n plus 5 and then.
So it would be yes, n plus 5 and then n minus 9. Is it still, yeah, is it still making sense to you or has it gotten harder? Okay. It would be a very short chart. What two numbers multiply up to -2 and add up to 1? -1 and +2. When I started the chart with A1, so I can go straight to factored form. It's going to be m minus 1, m plus 2, but you can't forget that the 6 that was in front needs to drop down. Elsie, you seem fixated?
No, I'm saying.
Life?
Oh, I don't like the next one.
Ooh! You want to try this one or are you scared of this one? Scared of that one? Can we at least agree on what the GCF is together? What's the greatest common factor here? 2, yeah. So if I bring out the 2, that leaves me m squared minus 17m plus 70. So now when I identify A, B, and C, LC, no distractions. So can we think of two numbers that multiply to give us 70 and add up to -17? All the numbers I know that multiply to give you 70 are 1 and 70, 2 and 35, 3 no, 4 no. And look, and if you're ever not sure, use a calculator and divide. 70 divided by 3, 70 divided by 4, 70 divided by 5. 5 does work. Huh?
5 and 14.
Yeah, 5 and 14, 7 and 10. In this case, what's the sign distribution going to be? No. When the multiplication column is positive, Emma. Very good. Both negative. Emma. Everything is negative. And since A was 1 before I started, I can go straight into factored form. That's going to be m minus 7, m minus 10. But, I guess I get 2. 4 more. What? What's it for? From what I can see, a lot of them are short. Because here, how many terms do I have? Yeah, so and look, this is to the 7th power. But whatever, it's. What's the GCF here? Yeah, they definitely have a 7. Since the lead is negative, you would probably see it as a -7. And then they both at least have a single x. So I bring out the GCF, -7x. -7x times what gives you?
6.
Not x to the 7.
X to the 6.
X to the 6. -7x times 3 gives us the -21x. The only thing that could possibly be is a difference of squares. It's not a difference. 3 is not a perfect square, so we're done. With 2 terms, that's the only other thing we can have. Hey, Soha. This will be hardest of the ones that remain. There is no GCF here, sadly.
Huh?
There is no GCF. Those cannot be divided by 3. And since 8 is neither perfect, it's negative, 3 is not perfect, like the only thing you do here is a chart. But notice, what's A going to be? A is going to be 3, so we're going to have to do that extra step that we did at the end, which makes it super hard. A times C is negative 24. B is negative 10. LC, when both columns are negative, what am I going to do with my factors?
Small plus.
Good. So I'll put my factors first. 1 and 24, 2 and 12, 3 and 8, 4 and 6. But then after I'll come in and say, okay, so the smaller one positive and the bigger one negative. Do any of those add up to negative 10?
No. No. Yeah.
Which one of those adds up to negative 10?
Oh, the 2.
Positive 2 and negative 12. So this is my winning combination. But then now remember that extra step. No, I didn't want to learn anymore. I still have my 2 parentheses, and it's still going to end up in plus 2 and minus 12. But don't just lazily put an x in front. Put a 3x in front. But even then, that's just temporary. Because now we got to go back and check.
Divide the thing by 3.
Does 3x and 2 have a common factor?
Nope.
No, so that's just going to drop down. 3x and negative 12 have a common factor. Yeah, they can both be divided by 3. So the 3x plus 2 comes down. 3x divided by 3 is x. Negative 12 divided by 3 is negative 4. This one should take you about maybe 3 seconds. There is no GCF, there's only 2 terms, and this is clearly a difference of squares. You have the difference in the middle. What times itself gives you x squared? X. X times x is x squared. What times itself gives you 16? So then all you have to do is remember the formula. Somebody impress me and tell me, even after this long, boring lecture, what does the difference of squares look like in factored form?
X minus 4.
What does a difference of squares look like in factored form? If only it had a name and I wrote that name down. Conjugate, good. So it'll just be x plus 4, x minus 4. That's the formula for difference of squares. And we finally made it.
Yeah.
We're gonna have over an hour.
2 times 2.
Yeah, there's no, but look, you gotta check for GCF first. Don't get lazy. This is a difference. Can I multiply anything times itself to get 4x squared? 2x. Can I multiply anything times itself to get 25?
Yes.
So then the only other thing is remembering what does a difference of squares look like in factored form? Conjugates. 2x plus 5, 2x minus 5. And then we celebrate.
Yay, we're done. Let's go.
Thank God.
Let's go.